This conference will now be recorded.
Can everybody see my screen?
Yes.
Yes.
So-
Perfect.
Yes.
Yes.
So today the session is about, okay. Today the session is about unsupervised learning. Can you tell me what makes something unsupervised? What makes something unsupervised? What's the difference between supervised and unsupervised?
Like you don't have the classes, the specific classes to.
Yeah, the labels. When we have a
Yeah.
data set such as this one, I'm going to draw again. We have like a data set here. These are the features. Height, weight, income, whatever. And generally we have here the class. In the unsupervised learning, we don't have this. We only have the features. Or you can call them the independent variable. We don't try to predict anything here. So you can tell me why bothering doing such thing. We want, with the unsupervised learning, we want to find out if there is or there are like multiple interesting structures in the data. Does it like the data follow certain pattern? Well, or we can call that a probabilistic distribution. For example, this one, we have this data, and we can see if we want to use clustering. Clustering is one aspect of unsupervised learning. Yeah, and it's not the only one. We have multiple ways of doing unsupervised learning. We have these data points. How many variables do we have? How many features?
2.
Exactly. We have 2 features. When we translate this into like the data set, it will be something like that. Size, which is this one, and whatever this one is going to be here. So this is my data set. It's just 2 features. That's why I can represent it into a 2-dimensional space. And we can see how can we, what structure, interesting structure we can find. We can find this one here. Like we have some data points that are following a line here, and other data points are following a different line. We can also find this structure. These data points are close, like this, here, and here. So we, of course, with the unsupervised learning, we have multiple ways of doing things. It's like the solution can have like different shapes. Give me 1 second. One learner is struggling to connect. Just 1 second. Someone is.
This conference will now be recorded.
So you can see, guys, with the unsupervised learning, we have multiple ways of clustering things. It's not one single solution. And the goal is very vague. It's vaguely defined. We just want to find some interesting structures and then see later if they can be useful or not. And remember this, we will need this concept till the end. Even in the NLP, it's strongly used. The NLP part is strongly used and very, very important. For example, here we can have this type of clustering. We have the genes, different genes, and we cluster them based on some similarity. So we can divide them in 7 clusters, genes that are represented in this way. I will have a different way, and we can see they have like similar patterns. And these are for individuals. So we can have a person with this or any kind of species that has this kind of genes, this representation. We can have this. We can see that the patterns in one per cluster are very similar. In clustering algorithms, we have three main families. We have a hierarchical, partitional, and Bayesian. Today, we are going to look into one of the most used algorithm for clustering. It is called K-mean. You probably heard about it. So hierarchical builds a hierarchy of clusters in a successive way. So we have here, we will have like a big hierarchy, like two big clusters, and then we keep dividing them until we reach the end. It can be top down or bottom up. Partitional, it determines all clusters at once. It's like it goes and divide all the data points at once. And Bayesian generate like a posteriori distribution over the clusters. It's like it finds like what rule a particular cluster is following, what probabilistic rule. Let's go to K-mean. K-means. It belongs to the centroid approach in the partitional family. It belongs to the centroids. Why? Let's see why. The K-mean algorithm partitions the data into K clusters, where each cluster is represented by a centroid. This is the algorithm. You have to provide the K. It's just a number, a positive number, natural number. You have to determine it yourself. Then choose K random data points. Choose K random data points to be the initial centroids. Assign each data point to the closest centroid. So it's like we have my data set here, and we have to put the centroid. The centroid is the center of a cluster. It's the center of a cluster. So if we say we want to divide this cluster into three clusters, we put the centroid randomly. For example, one in here, one in here, and one in here. And then assign each data point to the closest cluster. So this data point will be assigned to what cluster? Let's call them A, B, C. These are my centroids. This data point is going to be assigned to what cluster? A, B, or C?
A.
Exactly, the closest one. It's going to go to A. This one as well. This one will go to C. This one will go to B, and this one. So we end up with three clusters. And then we recompute the cluster again, the centroid, sorry, again. So we have three data points, or two. The centroid was here. In these two data points, we compute a new centroid, which is like the average between this point. The average between, where is it? The average point between these two? Somewhere in here.
Somewhere in the middle.
Exactly, yeah. Same for this, we'll go here. So A will go here, B will go here, C will go exactly here in the point because we have only one point. And then we do the same thing again. We recompute the distance. So the A moved here, B moved here, and C moved here. We do the same. I'm going to give you a better example that is like more visually appealing than my drawing. And we do it this again until there is some stopping criterion, or just one criterion. Let's see visually how this works. So also we have the stopping criteria. When do we stop? There is no change to the centroids. The centroids are, when in the next iteration, the centroids stay the same. They don't move. Or there is this change is very minimal. Or no reassignment of data points to new centroids. It means even if the centroid has changed, but the clusters The data points that belong to a cluster, they didn't change. They stayed the same mostly. Or there is this that we are going to examine later, minimum decrease in the sum of squared errors. We are going to see what is this later. Let's see this example. So we have these data points. What K did we pick here, guys? What is the K, our K?
3.
Exactly. 3, because these are the centroids. These are the centroids. So we placed them initially randomly. And then we build our cluster based on what is the closest thing for data points to my centroid. So we end up with something like this. So this ones will belong to here. This data points will belong to this cluster. And these data points will belong as well to this cluster. Then what do? We recompute the new centroids. So what they are going to do, they will move. They will move to the middle, more or less, because we average all the points and we see what is like the gravity center of these data points. So it will move somewhere in here. Same, this one will move somewhere in here, and this one will move somewhere around here. And so the centroids moved, and then we recompute the distances, and we see we get by like the new clusters will be modified a little bit. This one might now belong to this cluster instead, because this centroid moved here. This one might belong to this now, and this one, maybe this point, I don't know, might belong here. So we can end up with something like this. And we repeat this until my centroids or my data or the points don't change their clusters. Is it fine? Is it clear for you guys? It's a very simple algorithm.
Yes, Reda, but here there is a problem of K. The choose the good
exactly.
K.
You have to find it. K, you have to find it yourself. In some problems, or in many problems even, we don't know what is the best K. In some problems we can know it. I will show you some examples. But in some problems we don't really know it. We have to try, see, examine the data. Does it work for us or no, etc. But do you understand how the algorithm works?
Yes, yes, of course.
Perfect. Let's just see, do you think this algorithm is fast or slow?
It's slow?
No, it's rather fast. It's not an NP-hard problem. It's just some iterations until we find the stability.
But if we have many features, it's like it takes time to choose the K, and after
features will influence, of course. Features will influence, but problems that take most times are the NP-hard class of problems, where it's like it's not an iterative solution. Iterative solutions tend to be fast, but problems like, say, what we did in the past, like well, an SVM has an iterative solution. Like if we want to find the global minimum for a neural network, that's an NP-hard problem. It's difficult to find the global minimum or the best solution. But this algorithm is iterative. Generally, iterative algorithms are not bad in terms of speed, because it depends on T, is the number of iterations that we are going to need to have. K, the number of features. Sorry, no, K, the number of clusters, and the number of data points. Of course, the number of features is also important. And generally, K and T are small. So the algorithm is close to bilinear. It's considered as a fast algorithm. In practice, it doesn't take a lot of time to converge and find the clusters. The problem as well is that it terminates to a local optimum. Can you explain to me what this is? Why does it terminate to a local optimum? It doesn't find the best clusters usually. It finds good enough clusters. Guys, if you understood things to this bit, it's fine. Now it's a little bit more advanced stuff. So if you are going to struggle here, it's totally fine. Don't worry. You will understand these things little by little. Okay. So what does it mean? It terminates to a local optimum. This algorithm, I'm going to draw. What it does, it tries to find the centroids. I would rather not draw. Let's look at some graphs. It's trying to find 3 centroids where the distance between the point and the centroid is minimal. It's trying to find the minimum distance between the data points and their centroids. Same here. It tries to find the minimal distance, if, for example, the centroid is here, and this one is here. The distance between them is very far. Do you agree? If we go, this one, if it is here, C1 is here, C2 is here, and C3 is here. What is the better solution? This one or this one? The red one or the black one?
Black one.
Exactly, the black one, because the distance between each point and its centroid is smaller than this distance between these points and their centroids. So K-mean is trying to find what are the best centroids that minimize the distance between their data points and the centroid that we found. But because the algorithm is iterative, it doesn't usually find the best way. It finds like a good enough solution. I'm going to explain that later when we reach neural networks and deep learning, etc. We are going to explain this even better. But now let's just remember that it doesn't find the best solution. It finds a good enough one.
So it's like the more it iterates, the more it gets better, or it gets accurate.
That's true. The more it iterates, the more it gets better. But that's not the end of the story. It might not even find the best solution. Even if you make it infinity.
It may diverge as well.
It might not really diverge. Just to draw it again. Let's say that this function that we are trying to optimize is like this. I don't want to go here, but it's like this. If we start here, we are going to end here. But we don't know if there is a better solution here.
Yeah, like local optimum.
Yeah, guys, don't worry if you don't get it here. That's totally fine. We are going to examine these concepts later deeply. I just want you to understand what this K-mean, how this K-mean is working.
Okay, that's clear. Thanks.
Good. So it terminates to a local optimum. So, and the starting point is what determines what kind of solution you are going to reach. So it's good to try different starting points and see what is the best solution for you, because it can have multiple solutions depending on where you start. Starting points mean where you initially put the centroids. So it can be different. One of the problems is that the users need to specify the K. The algorithm is also, this is a drawback, is sensitive to the outliers. And outliers are data points that are far from other data points. So they influence where the centroid is going to be, of course. And what is also one of the characteristics of this algorithm is that it is good at detecting clusters of hyperspheres. What does it mean? This is what looks like a hypersphere. The clusters that K-mean find, the clusters that K-mean is going to find, will have a shape like this. It's like near to a sphere, close to a sphere. like here, here, here. These are close to a sphere. What do you think, guys?
Yeah, true.
So the clustering for k-means is always going to look like something like that. But many problems don't have this kind of patterns, like this one. We have, for example, these data points. When we run k-means here, what happens? It clusters it like this, because the clusters will always look like a sphere, like here and here. But we might need something different, like this one. Like maybe we want this type of clustering. And k-mean will never be able to do that. K-means will do something like this, here and here. It works well for this kind of problems. And a lot of problems are shaped that way. But some problems might be shaped that way. For example, another algorithm called dbScan is more suitable for this kind of problems. Density-based something, for example. And we have multiple algorithms. Any questions so far, guys? Is it clear for you?
Yeah, it's clear.
Yes, so far.
Okay, one question. Does it always converge, or it can go to infinity? Like this point will keep moving, like, for example, circling around. And what do you think?
In my personal view, I think sometimes it get away. I don't know.
It can diverge. No,
Yeah.
it always converge. Then you are safe from this side. And there is a mathematical proof. It's beyond the scope of today's session. I don't want to go into the mathematical proof, but there is a clear mathematical proof that k-means always converge. It will always reach a destination and stops there, which is safe, which is good. Yeah. So I want to give you an exercise for, say, you do it in 2-3 weeks. So I want you, I know it might sound a bit too advanced for some, but don't worry about this. We can help. So let's see, we have this image. It has a number of colors. And we want to convert it into an image of 16 colors, like in here, or just 2 colors. How would you do that? Let's say you want to convert this image into a black and white color. How would you do it?
Shades.
Sorry, what?
You would use shades in that, like same shade. It's like the nearest color to it. If you have 2 colors, you would just classify them to the black.
Yeah, you can do that. Like it is coded in RGB. Each color is some number, and you have the black, you have the white, and the color that is closest to the white becomes white. The color that is closest to the black becomes black. That is a possibility, but it doesn't produce the best result generally. This technique doesn't do the best, because colors can shift. For example, if most colors are close to black, the whole image becomes black. If most colors are close to white, the whole image becomes white. And it is not a really good solution, don't you think?
Would you do it by intensity? Color intensity?
Well, yeah, the color its intensity is defined by an intensity, of course. It's RGB or any other representation. We can use k-mean for this. This image was converted using k-mean from this color space to just 16 colors. It doesn't look too bad. What do you think, guys? This is from probably some 16 bits colors here, like 600 over 600,000 colors, and here we converted it on only to 16 colors, just 16. Does it look bad, or what do you think?
So the K is 16.
The K is 16 exactly. So we took all the colors here and converted this, like we clustered all the colors. We have a lot of colors here, and we clustered them into 16 colors, and they repainted them by their centroid. The centroid color will take the general color of all the other points, all the other colors. Did you get what I mean?
Yes, but the answer here, the input, it will be a matrix, or the matrix, or it's a different
the input,
line.
Yeah, the input is a matrix, but you can see it as each data point is 1 pixel. Yeah, each data point is 1 pixel. Yeah, and then we clustered all the pixels, like we group the pixels into 16 groups, and each group will receive the color of its centroid. We end up with something like that. It doesn't look bad. It's like slightly better than this one. What do you think, guys?
Yeah.
Even if you transform it, I did it many years ago, transforming images in just black and white colors, not grayscale, black and white, using K-mean, and pictures of people, and the result of like faces were really recognizable. Only black and white. You could really recognize the person. I remember I showed the picture of a friend, like using K-mean and transforming his face into black and white, and he was very surprised by, like, he still could, because he could recognize himself still, just by converting his picture in black and white. So this is the exercise. You have like 2-3 weeks. Don't worry, guys. This kind of learning is based on this method. You have you will struggle a little bit to understand how to encode your color and how to do the different pre-processing, etc. But once you finish the work and you get your results, you will learn a lot of things. Do you agree?
Sorry,
Yeah,
sorry, what was the exercise? Is it converting it to black and white?
Converting it into a number of colors. It could be black and white, or it could be just a number of colors using
any K that we choose, right?
Exactly. Yeah, it doesn't really matter. K is okay. Are you happy with this exercise, guys?
Yes. Yeah.
Yeah, sounds great.
Perfect. Now, let's see at the optimization properties of K-mean. So here we are. K-mean is trying, like I said, to minimize the distance between a point, between the data point that belongs to the cluster and this, the centroid. It's a little bit something like that. It minimizes the sum. Let's call this D. This is the distance of my data point, X. Let's call it X1 I C1. And C moves like it's a sum until Xn I Cn. This is a sum, so I shouldn't do this. So we sum this, the distance between each centroid and the points that belongs to that cluster, and it is trying to minimize this. Does it make sense for you guys? This is the mathematical formulation. Are you happy with this?
Yes.
All of you?
Yeah, I do have a question here. Is this like predefined function that we use, or we need to program everything from scratch?
Oh, generally when you work with K-mean, it's just a couple of lines of code. You just prepare your data when you use libraries, for example, scikit. When you use it, it's just a couple of lines of code, and it produces for you all the clusters. So you don't really have to worry about this. But it's really very good to understand what is happening inside.
Okay, so yes, you need also, I think, to know the libraries that exist.
Yeah, it's very simple. Scikit from Google is one of the most used libraries, and it does a very good job. But why we are going a little bit into the properties? It's because of interviewing questions. It's not just training here to know how to use a library, but in most interview questions, they want you to know these things a little bit in depth.
Oh, okay, great.
It's very important to have some depth in your knowledge. And you will know, and when you have some depth, you will know why your algorithm is not working as you intended, as it was intended. So you can see how your data are, or maybe it's not shaped. Your clusters shouldn't take centroid or hypersphere shapes, this kind of properties. So K-mean is trying to optimize this sum to make it as small as possible. And because it's an iterative algorithm, and it depends on the starting points of the C's, it doesn't find usually the best sum. It finds a good enough solution. And that's why it's good to run different iterations and see with randomly put in C's, these centroids, putting them randomly here, here, and here, and seeing how the solution is, or measuring this measuring this, and see what solution is the best. But in many cases, even the good enough solutions are good. Even like the non-optimal solutions can be good enough. Okay, are you happy with K-mean? Are you happy with this explanation?
Yeah, seems fair enough.
Yes.
So in like 2-3 weeks, guys, I can help. When you start working on this, don't hesitate to email me to give me your results, how things are working for you, etc. And because in the first 2 sessions on deep learning, the next 2 sessions, we will not do a lot of practice. It's mainly like we build our theoretical knowledge, and after this we can start practice. So this is the practice for like the next 2 to 3 weeks. Great. So this is for K-mean. We have a lot of different algorithms for clustering. The second most used is probably the hierarchical, and we have different other clustering here. You can have a look. We don't have, of course, time to look at all these methods, but you can have a look at them. Now, another technique for...
Reza, excuse me. Excuse me, that exists now, I think, dynamic K-means, no?
It has a lot of variations. It has many variations. It has a lot of variations, and you can use even like this iterative algorithm. We have multiple ones. There is not one single implementation for this, but like the basics are like of the algorithms is this one. This is the basics. Now let's have a look at another aspect of dimensionality reduction.
I'm sorry to come back to you again regarding the image that you've been talking about our exercise in 3 weeks. Do we use the same images, or will you send us the link, or maybe take another image?
Any image. It should be like work. It should work with any images. In the beginning, if you struggle a little bit, you can use any image you choose. It doesn't really matter. But ideally, your algorithm, your implementation should work with any image.
Noted.
Right. So now let's look at another aspect of dimensionality reduction. It's another aspect of unsupervised learning. We have clustering, which is a family of many algorithms, and we have dimensionality reduction. We have dimensionality reduction, which is also unsupervised. What it does, it reduces the number of features without losing information. It's like you have here your data set. Do you have a label or not? Do you have a label?
No.
Yeah, not necessarily. We don't need a label. We just have our features. Say we have n features, and dimensionality reduction will reduce them. Make them, for example, it removes this number, converts them into m features. M is smaller than n, but it keeps the same information. It means that the quality of M, of the new data set, is not lower than the original data set. What does it mean? Also, the most used by far, the most technique in dimensionality reduction is the PCA. It's by far the most used technique. Principal component analysis. So here, let's say we have a data set. As you can see, this is our data set. How many features do we have again?
2 features.
Just 2 features, exactly. One here and one here. And all of these points represent, each point represents one row of my data set. We can see that this feature and this feature are correlated. They are correlated. Do you think they are or not?
They are.
Yes, highly correlated. Yeah.
Yeah. When one feature like moves up, the other one it will move up as well. Same. If one feature moves down, the other feature is going to move down because we have something like that. Principal component analysis, what it does, it tries to transform my features based on the original ones. It's like transforming my reference. The reference here is this one. This is the vector that represents this feature, and this is the vector that represents this feature. It transforms it to this reference. It's like it rotates it and transforms it here. So the value of each point will be now represented here through this axis. So the axis will be this one now and this one, which means the amount of information now in here will be very small, and this one will be very big. The amount of information, like when we project, for example, this point here, it will go here and here. It's like a reference transformation. You used to do it in high school, guys. Do you remember this? In geometry, most of you have used this like reference transformation. We have this reference and we transform it to another one. Do you remember this concept?
Yes, that was basically in high school or
yeah, high school or before something. Yeah, something very early. So this is what we are doing in PCA, principal component analysis. This is really one of my favorite algorithms in dimensionality reduction. Can we change the origin or the reference, yet keeping the variance? Why do we want to keep the variance, guys? Tell me why. Why do we want to keep the variance?
To keep the first characteristic of the system.
Great, yeah. This is why the variance is what allows you to make the difference. For example, this variance is what allows. So, for example, let's have 2 features. A data set with just 2 features, x1 and x2. x1 are all 0. x2, we have some numbers, 2, 5, 1, 6. can we use x1 to make the difference between my my rows, my samples? Can we use x1?
No.
It doesn't contain any information. It doesn't make any difference between them. For example, like if we have like twins, identical twins, we can't distinguish between them generally. It's because there is no variance. All the features are the same. Variance is almost zero between these two twins, or one twins, or I don't know how to say it. So we need to keep the variance, the differences between them. So the PCA is trying to transform this into one variable, or a number of variables that is smaller than the original one, but it keeps all the differences. The variance is kept, like in here. So if we transform this data points from like this two-dimensional space into one-dimensional thing in here along this line. So this point will go here, this point will go here, this point will go here. We end up with something like that. And if we project to something that is perpendicular to this, U1, which is U2, we project things in here. This one will go here, this one will go here. So the variance here is very small, but the variance here is big. You can see the difference of values is very big here, and the difference in values is very small here. So most information will be contained along U1. Let's call this U2. Most information is contained here along this line, U1. And very little information is contained in here, in U2. So if we take only the projection of this point in U1, we removed one dimension, one whole dimension, but the information is almost the same. The information here is almost the same. Any question, guys, so far?
Rita, sorry, the variance is not like the characteristic that help us to see how our data points are far from the mean?
Yes, how far are they? Yeah, from the mean.
From the mean. So yeah. Here is like when we do projection, it's like we keep the mean or what? I don't understand.
When we do the projection, we try to find the maximum variance.
Okay.
The maximum variance that we can have. So the sum of the differences from the mean is higher along this line.
Okay.
But very small along this line. So that's why this line will maximize my variance. The sum, the difference between the mean and each data point. So we can remove this. So like when we convert my data to along U1 and U2, we didn't do a lot of work. It's not different from X1 and X2. We just rotated this X1 and X2 that way. We just rotated it. So it's just transformation of values. But if we remove U2, U1 will still contain most information, but we have only one dimension now. It makes things much simpler, but we have only one dimension. We reduce the dimension without losing information. This is what is happening.
Okay, got it.
Also, X1 and X2 are strongly correlated, as you can see here. Dimensional reduction also removes correlated, or PCA removes the correlation between the new reference. X1 and X2, or U1 and U2, will not be very correlated. There won't be a lot of correlation between them. It also removes correlation. A question for you guys. Which projection is better if we want to reduce this to just one dimension? This one, the left one, or the right one?
Left one.
Yeah,
The
exactly.
left.
The left one contains most of the variance. The right one is containing very little variance. It's a very bad one. But the left one contains most of the variance. So this is what we want to do with PCA. How the algorithms work? It's not a very complex one. We have multiple algorithms here. We want to minimize this distance, D1, which is the distance between this and this. So this distance is x multiplied by u, mathematically. And we try to maximize this. We try to maximize this distance by minimizing this distance. Because this doesn't change, if we minimize this, D1, just triangle, x doesn't change. If we minimize D1, this one will go bigger. If we we go here, or we change u. If we change u here, minimizing this distance will make this go bigger. So we want to maximize this, and this will maximize the variance. This is just one way of doing it. This is the standard algorithm to compute the PCA. If you will struggle here, don't worry, guys. It's not super important at this point to understand deeply how this algorithm is working. What I want you to understand is what is the best U here, for example, how the PCA, what the PCA is doing, what is maximizing the variance. Here you will understand it little by little. So we standardize the data set, we normalize it. There are multiple ways of standardizing the data set. We have the data set here. We can just do minus the mean divided by the standard deviation. And we can standardize my data set. We do minus the mean and we divide it by the standard deviation. Then we calculate the covariance matrix for the features in the data set. So we compute the covariance matrix. The covariance matrix is just we have the features here, x1, not x, let's call it f1, f2. And then the covariance matrix is just the covariance between each feature, f1, f2, f2. So it gives you how, more or less, how correlated are these features between them. Here, how correlated is f1 and f2, for example, etc. Then, if you remember, this is a linear algebra aspect. Calculate the eigenvalues and eigenvectors. You probably did it at the university, but you don't remember. At least most folks I met, they don't remember this.
How do we say it in French? Eigenvalue?
Vector propre and valeur propre.
Okay, yeah.
Now you remember. So this is, we compute the eigenvalues and eigenvectors. If you are more French speaking, we call it vector propre and valeur propre. And then we sort the eigenvalues and their correspond. So we get for each vector, eigenvector, an eigenvalue, a value. And we sort all the vectors by their eigenvalue. The vector that contains most information is the one with the highest eigenvalue. And we pick K, we pick the best K eigenvalues, the highest ones, to form a matrix of eigenvectors. And we transform the original matrix, the original dataset, by some matrix multiplication with the eigenvectors matrix. Don't worry, guys, if you don't get it so far here or fully here, it's fine. I don't even want to go too deep into this, how this algorithm is, just to have an overview. that it is based on the eigenvectors and the eigenvalues. That's what I want you like to know. This is one of the algorithms to compute, to find this best, this, for example, 2 lines. To find these 2 lines, like 2 vectors. This is one of the algorithms. It costs a lot. This algorithm costs a lot. There are other algorithms that are iterative. This one, as you can see, is based on some matrix multiplications to find the eigenvalues and eigenvectors. But there are algorithms that are more iterative and they produce not an exact solution, but they produce a good enough solution. Any question, guys? Now we have here all my vectors that I found and sorted by their eigenvalues. So this one, the best direction is the first eigenvector. So we see that this first component is the one containing most of the variance. It's the equivalent of this one. When we do this, when we run this algorithm, don't worry about the algorithm. When we run it, we get these components, PC1, PC2, all the components, principal component 1. The first one will contain the highest variance. The second one will contain a bit less, etc. So we end up with this order of principal components. Suppose we have, like originally we had a data set containing 10 features. And the lightest ones will have a very small variance. So if we take, for example, this, and we remove this, will it make a big difference or not?
Say again. Sorry.
If we remove these vectors, these features, these new features, in the beginning we had a data set containing 10 features. We run the PCA. We ran the PCA and we ended up with this new 10 features. These features have like different variance. It could be the same variance along them. It could be anything. But when we run the PCA, we end up with a new data set. But this one will receive the highest variance, which is this one, PC1.
Mm-hmm.
PC2 will be here. We receive a little bit less of variance. So if we take 7 and we remove these 3, so my data set had 10, it will be now 7 dimensions. Will it make a big loss or is it fine?
Is it fine since they have like?
Yeah, we are not losing a lot of information.
Yeah.
We didn't lose a lot. But we still reduced my data set from 10 to 7 features. Originally, if we removed, for example, we just chopped just three like randomly 3 features. It is dangerous to do that. My original data set had 10 and we randomly removed 3 features. It would be dangerous to do this. We don't know what information they have. But here we know that they contain very little information. They contain very little information.
So whether we calculate for each features, PC1 and PC2 for other features, for second features, and so on.
Well, yeah, we can calculate the variance. The PCA will get you this. Will get you this new matrix from 10 dimensions to another 10 dimensions, but transform.
This is the first step.
Sorry?
This is the first step.
No, let's take it. This what I represented here is just the algorithm.
Okay.
But let's say when you run the PCA, you don't do it step by step. You call a function, and it gets you this new dimensions.
Okay.
It's very simple in practice. It gets you the 10 new dimensions. It also gives you the variance along each dimension.
Okay.
So what you do, you can see the variance here is less than 5%. Here it's 23% or 22. Here it's around 17%, etc. So you can sum up the variance. And here it's just like 2 or 3%. So if we remove this, here we will contain like over 90% of the variance, 90% of the information. So if we take off 3 dimensions and we keep only 7, we still have like the data set, the quality of the data set is not far from the original one. It's smaller, but it is not far from it. It's almost as good as the previous one. When we run a classification task on this one, the difference is not huge, but it will be faster because we have less dimensions. In some cases, in many cases, when, for example, we have 1,000 dimensions and we run the PCA, in practice, we can end up with 10 dimensions containing 90% of the variance or more. It happens a lot in many cases, guys. When you have, for example, like a matrix or data set containing 1,000 dimensions, you run the PCA and you can end up with 10 features containing only, or just 10 features containing more than 90% of the variance. And it reduces the computation by a lot, really a lot. In this example, like we have most of the variance is like in the top 7 or maybe top 4. Top 4 is containing a lot. But in some cases, it can be really extreme. It's not only that.
But excuse me, Reda, but here we have to fix the minimum of variance.
Yeah, you have to fix. I want like 90%. I want 80%. You have to fix a minimum, yeah, and see how many you want to take. Sorry?
As a person. Okay.
Yeah, as a person, you have to specify it. Yes.
Okay.
You have to specify how much variance you want to keep, and see how much reduction you can have.
Okay, thanks.
But it's not only that. Generally, noise has a low variance. Can you see that? Noise, in many cases, when you are measuring something, it has a low variance compared to the real information. What does it mean? What does it mean for you?
We'll take off the noise, we'll take off the bad features or the bad data points.
Exactly. If we take off the features with low variance, we might take off the noise. And in many cases, it can improve your classification results. You remove this, for example, it can happen. You remove, for example, these 3 components. You keep only this 7. And you find out that your classification, if you add the class feature and you try to run a classification based on the PCA instead of the original data set, you might end up with better results. It can happen. It can reduce the computation time, the complexity, and it can also reduce or improve the results when using the PCA. Are you happy with this explanation, guys? About the PCA?
Yes, thanks.
Reda, is it quick to execute or is it fast?
The PCA is generally quick because generally the algorithms used is not this one like I presented. This one is just the same like the original algorithm. There are multiple ways of executing the PCA, and we have like approximative ways, and they can produce almost perfect components, very close to this algorithm, but they can be very fast. So it's generally a fast algorithm, at least the ones we are using right now.
Reda, I have a question. Can we detect outliers using PCA?
Can we detect outliers? You mean outliers?
Yes.
If, for example, we have a point in here, and we want to use a PCA to detect if it is an outlier or not.
Yes.
Generally, yeah, that's a good question. If we have, for example, a point in here that is an outlier, or something in here, it will probably influence the PCA, but because the other points will have like some more influence than the outlier, then this point will not influence this U. It will slightly influence it. U is here. It might go slightly in here. And this point will go in here, probably. But its value along this will be still high. It seems the outliers can have some influence, and can be detected more easily. Here we have like most points are coming here, but the outlier is going to come here. Same for here, the outlier, but the outlier can be a point in here or a point in here. I think that it has some edge in detecting the outliers. There is a possibility. I haven't used it so far for detecting outliers, but in my opinion, it has a good outcome when we want to detect outliers. Because here, for example, if we look at the variance of all the data points here, they are very small, but the outlier will have a high value. Same goes in here. And you might try to remove them by the PCA if you want. Does it satisfy your answer? Your question, sorry?
Yes, but we maybe I want more detail. So if you know any technique they use to detect automatically the outliers, so it will be good.
Well, outlier detection is a research topic. It's not one, we will not find one answer. There is like a lot of researchers trying to detect outliers, and in different contexts. It's not just one context. So it's really a large topic, and there are many techniques to detect outliers. We can use, for example, here, as you said, dimensionality reduction. We can use, for example, Fourier transform, where we can see that the outliers can have a frequency. We can have, we can use, for example, like you mentioned last time, autoencoders, that we are going to see them next in the next chapters. Autoencoders cannot re-encode the outliers in the PCA as well, like as mentioned in here. If, for example, you have an outlier where the noise is very high, so it will go in here probably. If the outlier is because of the noise. When we remove this dimension that contains very little information, this will go here. What happened in this case is that this data point is not an outlier anymore. It came here. So and because outliers have different reasons, so it's a really big research topic. If you want to study it, you have to read a lot about different ways of removing outliers. One simple way that is known for removing outliers is because outliers are not very common. We have just few data points. Is to do sampling, randomly sampling things, and outliers will have a lower chance of being picked. They will be removed by the sampling. So this is really a research topic, and I would recommend that you study it thoroughly if you want to understand it in detail.
Okay, thank you.
Okay. Also, PCA may not fit my other cases. For example, this case. This case in here. Can we use the PCA to transform it into a new dimensions?
No, we can't use it. here in this case?
The PCA, what would be the solution of the PCA? What would be the solution using the PCA? Something, well, because it's a circle, it can be anything. It can be that way, that way. They are all good solutions, more or less. How would you reduce the dimension if we are transforming this 3D or 2D into one dimension? How would you transform it?
I think we need more than 2 vectors in this case.
You can make it, you can stretch this line, make it that way. Yes or no?
We take the center of this point.
No. You can take it. It's like you take it by your hand and you make it like a line. Do you see what I mean? Something like this.
Yeah.
We use what we call here the geodesical distance.
Transformation.
We transform it into a line. So this one will become 0. Here 1, 2, 3. It's because it follows an ellipse or a circle-like thing like this. So transforming it with the PCA doesn't really make sense. We have other methods. For example, isomap, geodesic distance. Isomap is more of a better fit for this kind of data. It takes a geodesic distance from this center and draw a circle like this. And this circle will become the new dimension. Do you get it, guys? Do you get what we want to do? And if we transform things into something, transform this line, this not a line, this kind of this shape of the data into something like this. We went from 2D representation to a one-dimensional representation. Can you see it, guys? Here, do you see it? Can you see what is happening here? What is this dimensionality reduction way? This other technique.
It's like we stretch it.
Exactly, we stretch the line. It was a circle, and we make it. It was circular. Now we make it a line, continuous line. And this is better for this case. The PCA is not. It will be a poor dimensional technique to be used here. This is a better way of doing things. We have others, MDS. MDS keeps the information about the pairwise distance. What does it mean? Let's so the distance between these points in 2D is known. So the distance between this and this, the distance between this and this, we know how far apart they are. So the MDS, what it tries to do is to transform these points, this 2D space, into a lower dimensional space, but it keeps the distance intact between all the points. The distance is the difference between the points. It's like how different they are from each other. So the MDS is doing this. We are not going to study the MDS here, just to know, but it exists and it keeps the distance between each pair of data points. Pairwise distance is kept. And this is like an important information in my data set. TSNI is also produced good. It's really good for visualization. When we visualize data, for example, we are in 100 dimensions, we apply a TSNI to them, and we get like just 2 or 3 dimensions. It keeps the shape of the data. And it is really good for visualization if you want to visualize some 100 dimensions into just 2, 3 dimensions. We have also the kernel PCA. The kernel PCA is like the PCA, what it does, it transforms linearly things. Things are linear. just projects each point linearly. Kernel PCA, it can do things non-linearly. It can, for example, do a circular projection like this, like here, like a circular, not like in a linear way. And it has like more application. It can, in many cases, it can produce better results. In deep learning, we will see what we call, I haven't mentioned it here, autoencoders. It's a deep learning technique, autoencoder. Sorry, my writing is awful here. We are going to see the autoencoders in deep learning. And it is very related to the PCA and the kernel PCA with this autoencoder. I think we have finished earlier than I anticipated. Do you have any question about the PCA, guys? And dimensionality reduction. Do you have any questions? Do you get what we are doing with dimensionality reduction, keeping the maximum? This is like the take, what you need to take from today's session. We want to keep the variance and reducing the dimensions. The variance is the information contained in my data set. And sometimes small variances across some features can represent noise, and removing them can prove useful and improve results. So this is the dimensionality reduction. Any questions, guys? For this, I have also an exercise for you that I will send. There will be a data set where you try to improve its classification by using dimensionality reduction. This will be a simple exercise. I will send you the data set and some skeleton of the source code, and you need to add a few things there. And you will need like to use dimensionality reduction to improve the classification. Are you happy with this, guys?
Yeah. If you can also send us more, let's say, some links to the libraries or
of course, yeah, sure.
Thanks. Yeah, that's
sure,
great.
Yeah, no problem. So no questions so far, guys. Are you happy with this? These are like very lightweight topic. We are going to start like a bit more difficult topics later. But if you are happy with these explanations about the PCA, about clustering, I'm happy with this.
Yeah, so far good. Thank you.
Reda, excuse me, just one question. So about when we calculate or when we apply this algorithm, and then the representation, the visualization, then we see it with the graph.
With what?
When we calculate, when we apply this algorithm, okay? So we have at the end we have other new matrix, okay? So when
new data set, yes,
yeah, and when we want to visualize yes, this data, we are making the same graph.
You want to visualize it in 2 dimensions or something like that? That's what you mean?
Yes. We can see the difference between.
Well, if it is originally 2 dimensions or 3 dimensions, you can see the difference. But if it was originally 100 dimensions, you cannot plot that in the original data set.
Okay.
You cannot see it. Yeah, it's impossible to visualize 100 dimensions. We are not equipped for that. But this PCA can be used if you can reduce it to 2 or 3 dimensions. You can use it for visualization. But what is mostly used for visualization is this method Tisney. It's used for visualization. It produced some interpretable visuals.
Okay, thanks.
Okay, guys, will you use PCA? Do you think, guys, in your projects? Do you think you will use it? If you have a project?
Yes.
Where do you think you are going to use it?
I think to optimize data or to reduce the dataset dimension, it's good. It's good to use PCA. Also
Yeah,
for noise cancellation, these kind of things, it's very good. Yes.
Yeah, one of the main areas where we use PCA is, for example, if you have 10,000 dimensions and your algorithm will struggle, your machine learning algorithm will struggle with that to process it. You can use the PCA, reduce it to 10, 100, and then start your classification or your regression or whatever, and you will have you keep the variance, and your algorithm will become much faster. Second thing, as Farouk said, you can remove the noise or maybe outliers if you try it, and you can see. Generally, how we do these things, we try, for example, take the data set, and we try, if we can, to produce some classifier or regression. We see the results. We apply the PCA then, and we take in the beginning just like 90% of the variance. We see the results, and we keep reducing the variance to 85%, 80%, and we can see an improvement in the results sometimes. And then after like maybe 80%, results will deteriorate. So this is how we do things generally. It's like we see what variance we need to remove to improve the results. And generally, this variance may represent noise. Of course, you have to watch out for if you are overfitting, if you are applying a lot of modification in this variance, or how much variance you want to take, you might overfit. So you have to be careful with this. So yeah, we finished earlier than I anticipated. So thank you, guys, and I hope you will, most of you will do this, especially this first example, where we use k-mean to reduce the number of colors. Please, if you need any help, don't hesitate to contact me. I can help you in any way you want. But as long as you do it, that would be really good. It's not very complex as a project, but it will be very good to try clustering in this kind of problems. So no questions so far, guys?
Thank you very much, Rida. I was going to ask what's the relation between k-means and PCA in using deep learning, but now I noticed the difference. I mean, the useless of this. In my project in image processing, we use sometimes PCA to reduce the number of features before starting the classification, so it's more clear now. Thank you.
Okay, that's good. Thank you. Any other questions, guys?
Just one more question. What will be next week's topic?
We will start with the neural networks next week.
Okay, sounds good. Thank you very much.
Okay. So thank you, guys, and have a good week, and see you next week.
Thank you, Rida.
Thank you.
Thank you. Bye-bye.
Thank you. Many thanks.
Thank you. Bye-bye.